Hi there, folks. Today we're looking at modeling polynomial functions. And really, the idea behind modeling polynomial functions is one, coming up with the equation of polynomial functions, so working backwards to that equation, but two, using those equations in a real-world type of context, okay? And so the first thing we want to look at here, it says just write the equation of the function. And so for this one, I have some of these critical values that I need. I have the three x-intercepts, and we'll make an assumption on this one that it is a cubic function, that it's an x to the third type of function, and that there's nothing else strange going on here. And so as we look at this one, we just kind of write this out backwards, going back to the factors. Before I would have the factors of this thing, and I would use that to get the x-intercepts. Well, now I have the x-intercepts, so what are the factors of the equation? And so if I look at something like this guy, I'm going to say y equals. If I have an x-intercept of -5, it means I must have the factor somewhere in here of x plus 5. Okay? And again, we'll assume that it has a multiplicity of 1, not something 3 or something crazy like that, based on the shape of this thing. The next one, once again, I see an x-intercept of -1, so that means I must have a factor of x plus 1. And then the last x-intercept, I have an x-intercept of 2, so I must have a factor of x minus 2. I'm just working backwards to these factors. And from here, if I were to multiply this out, I would get a cubic function that has those x-intercepts. But the question really becomes is, where does this 0, -2, where does the y-intercept come into play? Well, let me multiply this out. So if I multiply this out, notice I've left a little space here, very ominously. If I multiply out the second two, that's going to give me an x squared minus x minus 2. Again, you can take that off to the side. I just did that middle step of the -2x and the plus 1x in my head. And now I'm going to multiply this out. That involves distributing the x value and then the 5. So that's an x cubed. Okay. And then from here, it's just a little bit of simplifying. And what happens, if I were to kind of just look at this as at face value and say, okay, that's my equation, well, that equation, the problem with that equation is that it has a y-intercept of -10, and I'm only supposed to have a y-intercept of -2. And so the idea here is, yeah, I could multiply this out, but couldn't there be any value out front here that could change this thing? Like, if I put a 2 out front here, it wouldn't change the fact that I had it wouldn't change the x-intercepts, but it would change maybe the shape of the function a little bit, and it certainly changed the y-intercept. Or maybe if I had a -2 out here, it would change maybe the direction of opening, and it would change the shape a little bit, but it wouldn't change the x-intercept. So as I look at this, I could throw some value out front that multiplies by this whole thing, and it wouldn't change. It wouldn't make a difference in terms of the x-intercepts, but it would change the shape, and it would change that y value that I have. And so the idea here is that there's some a value that I have yet to identify, okay? And if there's an a value that I have yet to identify, when I get down to the end, I just have to identify an a value that makes this thing work, that essentially gives me this y-intercept of -2. And so if we think about what y-intercepts mean, remember a y-intercept, if I kind of think about this for a moment, the y-intercept is when I plug a 0 in for x. So if I plug a 0 in for x, that would give me a -10 in here. And when I plug that 0 in for x, this y-intercept is telling me that the y value should equal a -2. And now I just solve this for a. I divide each side by that -10. So I end up with a equals a positive 1/5. So going back up to here to this almost completed equation, well, this should be a positive 1/5 right here. Because if I multiply everything by 1/5, once again, it doesn't change the x-intercepts, but it gives me the right y-intercept. And the last thing I'm going to do is I'm just going to distribute that guy. So 1/5 x cubed plus 4/5 x squared minus 7/5 x minus 2. Now I have the x-intercepts that I need, and now I have the y-intercept that I need as well. Okay? If I look at this guy, same kind of thing here. I have this. I have the zeros given, which will give me the factors that I need, and then I might have to adjust that based on the y-intercept that I have. So let's start with the factors that I have. And again, there might be some unknown a value once again, and I kind of know that ahead of time. So now let's write down the factors. If x equals a -3, then x plus 3 must be a factor. If x equals a 1, then x minus 1 must be a factor. If x equals a 5, then x minus 5 must be a factor of this thing. Okay? And then I multiply this out. Let me do some multiplying. Again, it doesn't matter what order you multiply these in. I think most students are more comfortable multiplying out the second two first, because then they like to distribute the binomial to the trinomial. And of course, combine like terms. And as I look at this thing, it has the wrong y-intercept. Without any a value out front, this one's going to have a y-intercept of 15. So what I need to do is I come off to the side over here. I'm going to say, hey, let me plug a 0 in for x. When I do that, I get 15. And when I plug that 0 in for x, I should get a -60 for my y value. And now I can solve this for a. So essentially, to solve for a, I'm just using that y-intercept each time. I'm plugging a 0 in for x and the y value in for y, and then I can solve for a. I can figure out what that missing multiplier is. And so it looks like this. It's a -4 times this whole thing. And I am going to go ahead and distribute that guy to get my final answer here. Let me draw it up here a little bit. So y equals, that's going to be a -4x cubed plus 12x squared plus 52x minus 60. Okay? Because again, that multiplier doesn't change any of the x-intercepts. What it does is it affects the shape of this thing. It affects the y-intercept. Okay? All right, next we're going to look at identifying the polynomial based on a table of values, okay? And what we're going to do here, if it's not necessarily the intercepts, the only time we really do this by hand is if I'm given all the intercepts. If I have all the intercepts and I understand that it's the most basic version of that polynomial function, then I can just come up with the factors and then find the a values and the y-intercepts. But if I have a table of values, I'm going to use either a calculator or a computer to go ahead and calculate this thing for me. All right. The thing that the calculator and the computer won't do is it won't identify the degree of the function. We have to do that by hand. All right. And so what we do is we look for a common difference. If there's a first common difference, well, we know we have a linear function on our hands. And really, that's us identifying slope. When we look in a table and we look for the pattern in terms of we're increasing or decreasing by the same amount for y, that's us looking for a common difference. And we're looking for that first common difference, okay? A second common difference is if, like, we look for the common difference and it's not the same each time, but now we look for the differences of the difference, okay? And we look to see if there's a pattern there that gives me the same thing each time. And if that's not the same, then we go for the difference of the difference of the difference, okay? And so, this sounds complicated, but it's really not. I just start expanding this table out looking for a common difference. And so here's what this looks like. Basically, however many tries it takes, however many columns I have to come up with in order to find the common difference, that's the degree of the polynomial, okay? So if I get a common difference on the first try, on the first set of values, then it's a first degree. If it takes 2 sets of values, then it's a second degree. 3 sets, third degree, 4 sets, fourth degree, and so on and so forth. And so when I look at something like this guy, I'm looking for a common difference. I just look at the y values, okay? When we identified linear equations, we always looked at just seeing if the pattern was I'm adding the same thing each time. And so here I go down by 2. So I'm adding a -2. And then I went down by 2 again, that's a -2. Down by 2 again, that's a -2. Down by 2 again, that's a -2. That's the common difference. And since I have a common difference here, since it's adding the same value every time, I know this is linear, okay? And the reason that it's linear is because this, okay, gave me the common difference. It's my first attempt, okay? If these values are not different, then I would start looking at the differences between each of these. And if those are common, then it's a second, that's the second difference, then it would be a second degree. And I just keep going until I get the same, the common difference that's the same each time, all right? And so for this one, I could punch this into the calculator. And if I punch it into the calculator, of course, I'm going to do a linear regression. Okay. We don't really need to do that for this one. And I think it would be silly and kind of a waste of time for us to do that. We understand how linear functions work. This is y equals a -2x. And then I would just need to identify the y-intercept by continuing the pattern here. Ready? 0, 7. Okay, so plus 7. All right, don't forget about all the things that you already know how to do. All right, if you want to punch this into the calculator, I'll show you how to do it on the next one. All right, but this one is not worth it. All right, if it's a linear function, just do it by hand because you already know how to do those. Okay. If I look at this guy, again, looking for those differences, this one I might have to go to the calculator on. But right here, I look for the differences and I say, hey, the difference between this guy and this guy, well, that goes up 2, so that's a positive 2. And then it goes up from 4 to 7, it's up 3. Here it's up 4. And here it's up 5. And notice, I don't have a common difference here. It's not the same each time. I'm not adding the same thing each time. So this is not a linear function, all right? And so what we do is we keep going. We expand this out. Now I'm looking at the 2, 3, 4, 5, and I check for a common difference here. I say, hey, to get from 2 to 3 is a 1. To get from 3 to 4 is a 1. To get from 4 to 5 is a 1. Well, now I have a common difference. But notice it took 2 columns to do this. This is the first difference, and here's the second difference. And the one where I found commonality was the second difference. So this is a second degree polynomial, okay? This is a y equals ax squared plus bx plus c polynomial. And again, we already know how to do those on the calculator. It's a matter of doing a quadratic regression this time, or using Desmos. It's a matter of punching this thing in. So let's go and do that. Okay, so for this one, the first thing we want to do here is we're going to click on this little guy and we're going to add a table. And we're just going to punch in that same table that we had in our notes here. And the y values. And it plots these guys. We can, move around, zoom in and out to kind of see them a little bit better. But here's where the work we already did comes into play. All right, the Desmos graphing calculator has no way of knowing what kind of function this is supposed to be, and so it's only going to fit whatever function we tell it to fit to this thing. So if we tell it a linear function, it's going to try a linear function. Okay, it doesn't know any better at this point. So we have to specifically tell it that we already discovered that this thing was a quadratic function that was a second degree. So to do a second degree, it's y1. The little tilde symbol, and then I type in my generic form, ax squared plus bx plus c, but make sure each of those x's is an x1, remember? And the reason for that is because we want it to use the values from the table. And the values from the table, the x values from the table are listed as x sub 1, and the y values are listed as y sub 1, okay? And so when I do this, I punch the thing in, there it is, A, B, and C down here. So this is going to be y equals 0.5 x squared plus 0.5 x plus 1. Okay, so let me go jot that down. So here, let's see, I had y equals, it was a 0.5 x squared plus 0.5 x plus 1. Okay, and if you want to write those in terms of fractions, that would be fine as well. And so if I look at this next one, same kind of thing here. I look for the difference. So I say, okay, the difference from 3 to 3 is 0. The difference from 3 to 5 is a 2. That's up 2. The difference from 5 to 15 is up 10, and the difference from 15 to 39 is up 24. And if we look at that, that is not the same, so this is not a linear function. A linear function, I would get the same thing for each of these as I increased, okay? So I have to go to the next difference, and I say, okay, how about the difference between from 0 to 2? That's up 2. Here that's up 8, and here that's up 14. Well, that's still not the same. So if it had been the same this time, it would have been a second-degree polynomial. Since that's still not the same, I have to go to the next one. And I say, okay, let's try again. Let's see what happens. Here it's up 6, and then here it's also up 6. And so what I find is a common difference, but it wasn't until the third column that I found it. If it had been the same here, that's first degree, second degree. This means this is a third-degree polynomial, okay? And again, that's the information I have to identify ahead of time because the calculator or computer won't know that. I have to figure that out on my own and then tell the calculator or computer what to calculate. So let's head off and go ahead and calculate this. So once again, for this one, we hit the little plus, we add the table, and I just punch in the values that I had. And so once again, as I look at this thing, I can scroll around and see all the points that are kind of plotted here. I actually have to zoom out. And again, Desmos has no idea what kind of function this is meant to be. We have to tell it that we've already done the work on this. And we've already discovered that this thing is a cubic function next to the third function. And so as I punch this in, again, it's y1 tilde. And again, the only reason I'm using y1 instead of y is because that's how it's labeled in the table. And that's kind of telling Desmos to use the values from the table to approximate this. And then it's a x1 cubed this time plus b x1, and every x should be an x1, sorry, squared. And notice, instead of ABC, I now have ABCD. And if I had a fourth degree, it would be ABCDE. So I just keep tacking on values here in order to approximate this. Although you might have to be careful with E, you might have to use something else in case it recognizes E as the number E. Okay, so you might have to skip E and go right to F for this. Okay, and so here we can see that the function goes through all those exact points that I was looking for, and it spits out my A, B, and C. I've got so this is going to be y equals 1x cubed minus 8x squared plus 21x minus 15. So there's my A, B, C, and D values. Okay, so let's go jot this down. And so for all intensive purposes here, I've got y equals 1x cubed minus 8x squared plus 21x minus 15. And that's it. So again, we have to identify the degree ourselves, and really it's just finding the common difference. I keep finding the difference. I find the difference, and then I find the difference of the difference, and then I find the difference of that until I find a common difference. And however many rows that takes me, however many columns that takes me, that's the degree of the polynomial. If I look at this guy, so this is kind of using polynomial functions to model a certain situation. So in something like this guy, so I have a piece of cardboard that's 20 inches by 36 inches. Let me draw my piece of cardboard, of course. And again, it was 20 inches by 36 inches. And what I want to do is I want to cut the corner. So I'm going to cut a square out of each corner. And I want to cut all of those squares the same side. And then I'm going to fold up the tabs that are left to create a box with no top. Okay? And so the idea here is I'm cutting away at this corner. And I'm going to do the same thing to each of these corners. Okay? And I want to cut the same amount, the same size square from each corner. Okay? And so what happens is if I were to cut this, all right, imagine that this piece on this end, if each of these was gone, just pretend they're not there anymore, okay? What it does is it gives me like these little tabs right here. If I kind of draw that line, we can kind of see this guy right here as a tab, okay? And if I were to fold that tab up, it would give me one of the sides of the box. Same thing here. If I were to make a fold right here, and fold that side up, that little tab that's there, okay, it would give me another piece of the box. Same thing here and the same thing here, okay? And so maybe it would be better if I redrew the picture. But essentially, once I cut those little squares out, what I have is something that looks more like this, okay? And so here's what I'm talking about in terms of these tabs. So like this guy right here, if I were to kind of fold that up, that would be one of the sides of my box, okay? And hopefully you can kind of visualize that, kind of making folds and each of these things that I have squiggly lines on. Imagine those folding up off of this paper. Now I'm looking down into the bottom of the box, okay? And so what I want to do here is I want to calculate the volume of the box, but I want to maximize that volume, all right? And so I have to determine, well, what size cut should I make? And so the idea here is if I call that X, okay, so the size of the cut is X. I could visualize it over here as well, X, okay? That's the thing I have to be smart about. I have to make the right size cut in order to make the volume of this box the most it could possibly be, okay? And so now I need to think about the dimensions of the box itself. See, once I fold those tabs up, the box is not going to be as big as the original cardboard, okay? Because again, if all of these pieces represent X out here, okay, that means that the bottom of the box, the length of the box is this purple piece right here. Well, it was 36 inches, right? But then I cut a square away from each end. I cut X off of one end, and I cut X off the other end. So what I did was I reduced the length of this thing to 36 minus 2 of whatever I cut off, okay, because I cut it from each end. Likewise, the width of the box would be 20 minus 2x because I cut the same amount off of each end. And then think about the height of the box as I fold up these tabs. Think about what the height of the box would be. Well, that's the value of x, okay? So the height of the box is going to be whatever the size square that I cut, okay? And so if I think about this from the perspective of length, width, and height, the length of this thing is 36 minus 2x. The width is 20 minus 2x. And the height of the box is x. And so if I want the volume is length times width times height. And it doesn't matter what order I do these in. If I was writing a polynomial, I'd probably write it like this, with the x out front. And see, this is a situation where I can find the x-intercepts myself. I could find those as x equals 0, and x equals an 18, and x equals a 20, all right? Just by setting each of these factors equal to 0. And so now I want to draw just a quick sketch of this thing. Well, actually, I'll draw an accurate graph of this thing, but of course that starts with the quick sketch. So if I come down here and I start my quick sketch, so let's see, I've got x-intercepts of 0, 10, and 18. And then looking at the end behavior, this is an x to the third function with a leading coefficient if I multiply it out of positive 4. So a 4x to the third. And so that tells me the end behavior on this end, it's going down, and this end it's going up. So I know it's going to be something that looks like this. And then I go to either my graphing calculator or Desmos, and I find the rest of these values. I fill in the gaps. I get my accuracy. And when I do that, I'm not going to show it here because we should already know how to do that. But when we do that, I get 4.127, 1345. Down here, I get a 14.54, comma, negative 913.6. But now the question asks me to maximize the volume here. And as we look at this thing, the graph itself, the y values on this graph represent the volume because the v was what this thing was equal to right here. So v is the volume, so y is the volume essentially, and x is the size of that little square, the size of the cut that I'm going to make. But then the question is, if I want to maximize the volume, as we look at this thing, like here's a point that's higher than all the rest. Here's an even bigger point, an even bigger point, an even bigger point. If we start to think about this in terms of end behavior as x goes to infinity, f of x goes to infinity. So according to this function, the volume goes to infinity if I just make the cut infinitely large, okay? But the idea here is that's not realistic, okay? That's outside the realm of reality. Even just looking at a piece of this thing we have identified, like down here, the volume is negative 913.6. That doesn't even make sense. I can't have a negative volume. And so I have to kind of root this thing in reality. And if you look at this thing, let's think about the biggest cut that I can make. If I go back up to my picture. When you look at this thing, the cut that I make has to be smaller than a certain value. Obviously, the cut that I make has to be a positive value. If I don't use a positive value, I'm not cutting anything. So the cut that I make has to be bigger than 0, but it also has to be smaller than 10. And here's why. When I look at the smaller side of this thing right here, if I were to cut in 10 from this side and 10 from this side, what's going to happen? Well, I'm going to cut the whole tab off. I'm not even going to have anything that I can fold up to make a box, all right? So my cut has to be smaller than 10 in order for me to be left with something on that side to fold up, okay? And so when I kind of look at that in terms of this graph right here, I only want to look at this graph from the interval of 0 to 10. Okay, I only want to look at this chunk of the graph. I only want to look at this interval because that's the interval that's based on the reality of the situation, okay? And so if I want to maximize the volume, well, that means I'm looking for the relative maximum that exists within this realm of reality, all right? And for this particular example, that means making a cut of 4.127 inches. All right, so that's the cut that I want to make to maximize. And then if it asks for the volume that I'll get is the y value there, okay? So understanding those pieces and how to interpret them, I think this one just asks for the size of the cut, which should be 4.127 inches, which is about 4 1/8 of an inch, okay? And so again, we're using that idea of the polynomial describes the volume, all right? But not all of this polynomial is using realistic values. And that's why relative maximums and minimums become really important, because I'm looking for the intervals of the graph that are rooted in realistic answers, okay? And so when I do that, now the thing I'm looking for becomes a relative maximum, or in some other cases might be a relative minimum, okay?